In the endless void of night, the most primordial and icy remnants of the universe silently make their passage. When sky survey systems detected one of hundreds of new comets in the final days of 2019, scientists didn't know they had stumbled upon an extraordinary discovery. This object, officially designated C/2019Y4, but more strikingly known by its codename, Atlas, appeared at first like a typical celestial body. Yet, as the days turned into weeks, Atlas's behavior became increasingly erratic, almost like a signal of an uncontrolled force originating from the depths of space, alien to our usual predictability. A normal comet warms up as it approaches the sun, its ice sublimating to leave behind a magnificent tail. Atlas, however, defied this rule. Experts tracking its orbits noticed that the object was brightening much faster than expected. This luminosity increased rapidly, then unexpectedly waned. It was as if an unknown switch was being randomly flipped deep in space. As the scientific community struggled to grasp the true meaning of this sudden flare and the ensuing orbital instability, a whisper spread across the globe. The object's behavior was uncontrolled and unpredictable. This unpredictability created a terrifying zone of uncertainty in ATLAS's orbital mathematics. Normally, the orbits of celestial bodies can be calculated with millimeter precision using Newton's laws. But Atlas was constantly receiving small thrusts from jets of gas randomly erupting from its surface. These jets continuously, but unpredictably, altered the comet's direction and speed. This random walk in its orbit complicated the theoretical collision models. Despite being hundreds of millions of kilometers away, this small, icy chunk of rock placed the question, could it hit Earth? On the desks of scientists and into the minds of millions of people. Atlas became more than just a comet. It became a cosmic riddle. The observation data was inconsistent. Its brightness was fluctuating. Orbital predictions had to be constantly updated. This instability challenged modern astronomy's quest for certainty. It was as if the universe was showing us how fragile even our most precise mathematical laws are in the face of just a little bit of randomness. What is the truth behind this unexpected behavior? Is there a possibility of a collision, or are we merely witnessing nature's own lawlessness? Where is this mysterious and unstable celestial body taking us? The story of Atlas began with a small but powerful telescope located on Mount Haleakala in Hawaii. In December 2019, the Asteroid Terrestrial Impact Last Alert System, or simply the ATLAS project, captured it during its routine scans. Named after the Discovery Project, the object was initially catalogued as an ordinary long-period comet. Long-period comets originate from the vast, frozen expanse known as the Oort Cloud, far beyond the solar system. They awaken from their slumber of millions of years and embark on orbital journeys, sometimes lasting tens of thousands of years, to pass the sun just once. Atlas was one of them. When the initial data arrived, the comet's orbit turned out to be surprisingly familiar. Backward calculations indicated that Atlas shared a common lineage with the Great Comet observed some 5,000 years ago, around 3,960 BC. This suggested that ATLAS was the remnant of a fragmented parent body. Such fragmented objects are already considered inherently unstable. But Atlas's real dramatic story unfolded in February and March of 2020. When Atlas became far brighter than expected, the eyes of amateur and professional astronomers suddenly turned to it. Its brightness increased so rapidly that it was expected to become visible to the naked eye. Some forecasts even dubbed it the Comet of the Decade. At that point, the comet's nucleus, the solid core, had to be either larger than anticipated or incredibly active. As it approached Earth and the Sun, the ice and frozen gases on its surface began to sublimate. turning directly from solid to gas. These gases created a massive atmosphere, a coma around the comet, sometimes reaching a diameter larger than the planet Jupiter. However, this glorious ascent ended abruptly in April 2020. Telescope images showed a shocking sight. Atlas was disintegrating. The central nucleus had broken into multiple smaller fragments. This fragmentation was the final fate of large comets seen before. The object had either succumbed to the tidal forces brought on by approaching the sun, or had been ripped apart by internal pressure. The comet's nucleus, contrary to expectations, was not a strong piece of rock, but a very loosely bound icy rubble pile. This dramatic breakup completely altered the comet's orbital mathematics and fueled speculation about the collision risk. Did the fragmentation reduce the danger, or did it create a wider hazard zone? For science, this was a challenge to our understanding of cometary physics. The fragmentation of ATLAS and the instability in its orbit put established knowledge about such events back under the microscope in the scientific community. Comet breakups are not rare, but a sudden breakup like Atlas's, occurring so far from the sun, brought multiple possible scenarios to the forefront. To understand this situation, we must look at similar phenomena. For instance, the Shoemaker-Levy 9 comet, which impacted Jupiter in 1994, was captured by the giant planet's gravity and ripped into over 20 fragments. Atlas was not passing that close to Jupiter, which suggested its fragmentation was due to an internal cause. The strongest scientific explanation was the pressure from super-volatile gases accumulated within the comet's nucleus. The initial heat from the sun released these gases, like carbon monoxide, from the depths of the core, and this pressure tore apart the loosely packed rubble pile. This indicated that ATLAS was a fragile cosmic cotton candy. So, how did this situation affect the collision risk? The possible scenarios were grouped into two main categories: why a collision wouldn't happen and why it could. Why a collision wouldn't happen. The fragmentation essentially dispersed the comet's mass, turning it into an atmospheric hazard rather than a global annihilator. Each fragment was much smaller and more fragile than the original body. The probability of these fragments hitting Earth was spread out over a wider area compared to a single large object. Orbital modeling conducted after the breakup confirmed that the vast majority of the fragments would either vaporize in the inner solar system or remain millions of kilometers outside Earth's orbit. Therefore, the grand cosmic catastrophe scenario was effectively prevented by ATLAS's own fragility. The most frightening scenario was that one of the fragments would receive an unexpected gas jet thrust, changing its orbit directly toward Earth. While mathematically possible, this had an extremely low probability. Scientists continued to use telescopes to track any such random rogue fragment. Another low-probability scenario involved the dust and small debris created by the breakup intersecting Earth's orbit, leading to an intense meteor shower. This would create a visual spectacle, but would not pose a major threat at the surface level. Ultimately, the scientific data indicated that the danger posed by ATLAS was largely exaggerated, and the actual collision risk was close to zero. The story of Comet Atlas became a modern lesson at the intersection of scientific certainty and cosmic chance. In a short 4-month span, it went from a Comet of the Decade candidate to a fragmented, harmless pile of debris. The strongest likelihood was that the comet had a rubble pile structure, couldn't withstand the sun's heat, and disintegrated due to internal pressure. This essentially eliminated its threat. Even at its closest approach, it would have remained hundreds of millions of kilometers from Earth. Despite all the uncertainties, the math ultimately worked in our favor. However, Atlas didn't just tell scientists that the collision risk was low, it also demonstrated how limited our knowledge of cometary physics still is. Its unexpected brightening, subsequent breakup, and random orbital pushes prove that these primitive ice masses from the Oort Cloud still hold deep mysteries waiting to be solved. Atlas clearly showed that a comet's behavior is determined not only by gravity and velocity, but also by chaotic and unpredictable internal dynamics, such as gas outbursts at the atomic level. At this point, speculation inevitably arose. The comet's initial abnormal luminosity was interpreted by some as alien technology or an artificial propulsion force. The mysterious movements of other interstellar objects, like Oumuamua, continue to fuel such theories. But science speaks with data. In the case of ATLAS, the fragmentation largely undermined the alien theories. It would make little sense for an artificial craft to self-destruct at the most critical moment. While these theories are captivating, the simplest and strongest explanation is that ATLAS was merely an extremely active, highly fragile natural phenomenon. Atlas gave its lesson and silently retreated. Its story served as a reminder that there are forces in the universe that we cannot entirely control. Even the slightest gas puff from a comet's orbit can capture the attention of millions of people on Earth. Perhaps this was a warning, showing us not just grand catastrophes, but also our cosmic fragility. The heavens remain filled with mysteries waiting to be explored, and the next celestial body, much like ATLAS, might be waiting to surprise us once again. That comet continues to drift in fragments through the depths of the solar system, with the question of whether it will ever reassemble remaining unknown.